All right, ladies and gentlemen, class recording has started. So, let's go here. Maybe my pen actually shows up. There we go. All right. Wow. For like the 50th time, right? Chapter 2 and Chapter 3 deal with this idea of kinematics, where we're describing motion, but not exactly talking about why it happens. And in the course of our study of kinematics, we've come up with several terms and several ideas that we use to describe the motion of an object, such as, hold on one second, such as, what's one word that we can use to describe the motion of an object, or that we need to describe the motion of an object? Okay, let's go with velocity, right? Hold on one second. Okay, so even if you're watching the recording, that wasn't really a delay, but it was a delay for us. So, all right, so Brett, we talked about velocity, right? And velocity tells us what an object is doing, right? What else did we talk about? What other things do we need to know to describe the motion of an object? Position, right? Position tells us where something is, right? What else? Acceleration. Acceleration tells us what's going to happen next, right? And then the last thing, time. Time sort of brings it all together when all these things are happening. So we've talked about all these concepts here, okay? And section 3.2, the packet that we just started on Friday and will continue today, starts bringing all of these concepts together because velocity depends on position, or at least the change in the position. And velocity also depends on time. But then acceleration depends on velocity, or at least the change in velocity. So if you change one of these ideas, the other things start changing as well. But what we find out is that there are equations that represent the patterns of how one changes in relation to the other. And on Friday, we introduced these three equations that show the relationship between, first, right, velocity, time, and acceleration, right, where we can figure out how fast something will eventually be going if we know how fast it started going, and the acceleration and how long it goes. And then we talked about in the middle equation that if we know an object is changing velocity, as long as it's changing velocity at a consistent rate, a constant acceleration, we can figure out the average velocity of that object during a time frame just by taking the initial velocity, the final velocity, adding them together and dividing by 2, just like we calculate the acceleration for any object. And then the last one we talked about springs out of this equation that we introduced back in chapter 2 to show us the position of an object at any time as long as we knew the velocity. And the velocity of that object was always a constant velocity. But now that we got a changing velocity, if we just take this expression for average velocity and substitute it in here for this velocity, we end up with this equation that shows us where an object is even if its velocity is changing. Okay? Good there? And then on Friday, I believe we did this problem at the end of class. Is that correct? Okay. Quick example 3.7? Yeah, the graph is new, but we did this problem up at the top, right? Okay. And we talked about that the final velocity of this object, I believe, was positive 13.5, and that the final position of this object was 37.5. Is that correct? Those two? Okay. All right. So now let's build on that, okay? Down at the bottom of the screen, and you guys have this at the bottom of page 2 of your packet, we have a graph of velocity versus time that shows the increase in the speed of the boat that we calculated in our quick example 3.7. So I'm going to zoom in for you guys, and if you see it on the screen, you don't get to zoom in, but that's okay. All right. What we're going to talk about here is in by no ways intuitive, but it will take us from one equation to the next equation. So this graph of velocity versus time. We already learned that this graph of velocity versus time will tell us one thing. What's the one thing that we know the velocity time graph will tell us? Because of the slope. So the slope of this graph tells us acceleration. So based on the previous problem, we should know that the slope of this line is equal to what? 2.40 meters per second squared, and that's what it is if we calculate it. However, like we talked about with the position graph, the slope telling us the velocity, and the velocity graph, the slope telling us the acceleration, even though we may be graphing one thing, there are other relationships there that may tell us something different. And like I said, this is in no way intuitive, but follow me. In this picture, they have shaded two regions of the graph, one dark blue, one light blue. These two regions just so happen to fill up the space between the x-axis of this graph and the graph itself. So all of the area between the x-axis and the green graph itself is now filled in by these two shaded shapes. They broke it into two pretty regular shapes, a triangle, the light blue triangle on the top, and then the dark blue rectangle on the bottom. Now, again, in no way intuitive, but back in geometry, you learned about the area of certain shapes, or maybe even before geometry, I don't know, 5th grade or whatever, right? And you know that a rectangle, to find the area of the rectangle, it's base times height. The base of this rectangle runs along the x-axis of this graph. So the base of that rectangle represents 5 seconds worth of time. Yes? The height of this rectangle runs along the y-axis, and it just so happens to correspond with the initial velocity of that boat, which we learned in the last problem was 1.5 as it was rolling or coasting through the marina. If we take the base, a time, multiplied by the height, a velocity, we would get a distance. Okay? Yes, no, maybe? You want me to write it out, or? So, if we know that velocity equals displacement over time, oh my gosh, my pen is really badly, it's very poorly calibrated. I know, but I don't know how, hold on a second. All right, so, before we had that fascinating discussion that people watching the class recording will never know about, so Krista's going to be jealous because she might be the only one who actually watches this recording. But so anyway, we were talking about the idea that we could find the area of this rectangle, and the rectangle, right, has two sides where one of the sides is time. Oh, sorry. Let's talk about that in just a second. So that's, Kaylin, that's why here, with this, right, the base of this rectangle is representing a time, okay? And the height of this rectangle is representing a velocity, okay? If we do base times height, or velocity times time, that's the same as doing this times this, right? Does that make sense? Velocity times time, because that's what the two sides of that rectangle are representing. So if you multiply velocity times time, you end up with a displacement. And down here, right, it's showing you that displacement. That rectangle is representing how far that boat would go, even if it never sped up, right? Because the whole point of that question was, how far does it go while it's speeding up? Well, even if it would have never sped up, because it was moving, it still would have went a certain distance, and that distance was 7.5. But remember, when we looked at the pictures at the beginning of this chapter on acceleration, because the car or the guy on the bike or the stick figure, whatever one we looked at, was getting faster, remember that the distance between each picture kept getting bigger and bigger and bigger. And so the distance that it covers not only depends on how fast it was moving originally, but also how quickly is it gaining speed, and also how much speed is it gaining. The triangle, remember, 1/2 base times height for the area of a triangle. The base of that triangle is still representing a time. It's still 5 seconds. The height of this triangle now is representing the change in the velocity. How fast were we going down here to how fast are we going now up here? Good there? At least conceptually, right? When you multiply that out and find the area, again, it turns out to be a distance. If you add the two distances together, the rectangle representing how far it would have went even if it never sped up, the triangle representing how far did it go because it was going faster and faster and faster, you end up with 37.5, which in the previous problem was what we calculated was the distance it would travel using one of those previous formulas. Does that make sense? At least kind of? Not necessarily why we would do it, but it at least sort of makes sense. Yes, pretty much, yeah. So what this is going to get us to, Caitlin, is another way for us to figure out distance, knowing something else that we maybe don't know one thing, but we know something else, and I'll show you that formula. That's this dark blue. But if we also throw in the triangle, we get how far it actually went, including that acceleration that we calculated before. Brett, are you okay? Are you good? Okay. So, again, in no way intuitive. All right, I wouldn't expect you to figure that out on your own. But just to make connection, those of you that are in calculus, this is the concept of an integral. And you guys will learn about integrals later on in the year. And you'll do a problem similar to this later on in the year and go, oh, we kind of talked about that one day in, and that was a really bad class recording, and I remember that day. But when you get into integrals, you'll talk about this area between the x-axis and the graph itself and another way to calculate it. Here, all of our graphs are going to be straight lines because we have constant acceleration. So all of our shapes are going to be rectangles and triangles. But if you get a graph that isn't a straight line, if it's a curve of some sort, you have to have a way to find that area, and that's what an integral does. So you'll talk about derivatives and integrals, and that's the gist of an integral. Okay? Now, where does all this get to? All right. The bottom part, the rectangle, deals with the velocity it was going. The triangle up at the top includes the change in the velocity. And we know that the change in the velocity is required in order for there to be what? Change in velocity is acceleration. So now we're including the acceleration into that determination of the distance. Where does all this lead? It leads to the top of page 3 of your packet. There we go. That says position is related to acceleration and time. This formula relates together now where does an object end up, x final, versus where did it start, x initial, plus how fast was it going initially, v initial, and then there's an acceleration factor in there. There's one term that's missing from this equation that was in the previous equations that we've used. What term is missing out of this equation that we used in the previous 3? Anybody perceptive enough to pick it up? Simran, what is it? The final velocity doesn't show up anywhere in that equation. That's okay. Maybe we don't know the final velocity. Even if we don't know the final velocity, we still have a way now to figure out where does this object end up based on some other factors. Okay? So, guided example 3.8 says, a drag racer starts from rest and accelerates at 7.40 meters per second squared. How far will it travel in 1 second, 2 seconds, and 3 seconds? I won't do all three of these examples for you because they're all the same, just with different numbers. Right, go ahead. Hold on to that question just for a second. We'll talk about how it relates to this during this problem. Yeah? So, I won't do all three of them for you because they're all basically all these time. It's all the same calculation, just different numbers. So let's pick one time. What time do you want to figure out as far as figuring out 3 seconds? Brett's going big or going home. So, all right. So 3 seconds. Okay. So it says, drag racer starts from rest and accelerates at 7.40 meters per second squared. How far will it travel in 3 seconds? If it's asking us for how far will it travel, what does it want us to know? Final position, right? That's our unknown in this problem. Where does it end up? All right, we've established what we're looking for. Now, what do we know? So a couple things are obvious. What's one obvious thing that we know from this problem? That's not the obvious thing. Let's go obvious first, right? Right. Okay, the acceleration that they gave us is equal to 7.40 meters per second squared. Okay? What's the other, like, smack you in the face obvious thing? The time is going to be 3 seconds because that's the one we picked. Okay, so the point of doing this is not just to use this equation, which it is, but it's also to kind of talk about how do we get information that maybe we don't obviously see in the problem. Okay? So there's a couple more things that we need to know in order to use this equation that we just introduced, which, if they're on the same page, let's face it, I want you to use that equation, right? So, Simran, what's one thing that we can get out of there? Go ahead. Not necessarily, although, like we talked about on the last test, if it doesn't say specifically, we can sort of make that decision, whatever decision makes our lives easiest, okay? So, let's talk about the two other things that we don't know, and then we'll talk about making a decision to make our life easier, okay? So, right, the one thing you brought up before was what? Initial position shows up in this equation, so we need to know it if we're going to solve for final position. It makes our lives easier if we say that this drag racer started where? At the origin, right? Anything that we can make zero in a formula or in an equation just makes the equation easier to solve. So it doesn't tell us specifically where it started. Let's call it 0, then we don't have to worry about that, okay? The other piece of information that we can kind of infer from the problem, we don't have to make an assumption, it actually tells us in the problem, but not like straight away, is what? Initial velocity is going to be what in this problem? 0. If it's telling us that it starts from rest, right, that means that VI is equal to 0. Okay? So now, Simran, in this problem, because it's a drag racer starting from rest, physically what's going to happen to the car? It's going to do what? It's going to speed up, right? In this case, because we have an initial velocity of 0, it really doesn't matter which direction we go in. It's going to speed up anyway, but it's probably easier in this case if we make that acceleration positive. It just makes the math a little easier. That's about all. In that case, yes, because it really hasn't done it. Although the next problem we'll see that it does sort of dictate what we have to do based on the situation that we're dealing with. Okay. All right, so then, right, x final equals x initial plus VIT plus 1/2 AT squared. Based on the information that we got out of the problem, a couple of these things can go away. First, the initial position being 0 means that that term becomes 0. Right? Also, the initial velocity being 0, regardless of how many seconds we go, right? 0 times anything, that whole term becomes 0 as well. So then, this equation simplifies down to x final equals 1/2 at squared. Alright? And because we're solving for x final, we really don't have to rearrange this equation at all. The term we're solving for is already by itself on one side of the equation, so it's just a matter of plugging in numbers and getting a final position. So, anybody got the calculator out that they can run that through? Right, good. Say again? Okay. Everybody verify that, or? Okay, go ahead. Because we're multiplying. So why did we get rid of time after the initial velocity? It's not so much that we got rid of it, but what did we say the initial velocity was in this problem? 0. So because we're multiplying those two together, 0 multiplied by any time is just going to be 0 anyway, right? And that's, again, that's one of those things that if we can make things in the equation 0, either through assumption or through what the problem tells us, it just makes the equation a little easier to solve. All right, good there? And then technically similar, because we chose the acceleration to be positive, right, that this final position would be on the positive side of whatever starting point we picked. Good? Okay. On the top of page 4 of your packet, is another equation that relates together different things about kinematics, different descriptors of motion, and how if we change one, the others change. So, I'm not going to show you the derivation of this and where it comes from, because it's kind of complex, but we end up with an equation where Vf squared equals Vi squared plus 2a times x final minus x initial. Okay. If we look, similar to the previous equation, this equation is missing one of those kinematic descriptors that we've used throughout the rest of the problems. What's missing from this equation? Time is missing in this equation, right? Time doesn't show up anywhere. That's okay. Maybe we don't know the time. But if we know some of the other things about that motion, we can still solve for whatever it might be that we need to solve for. Right? So, right underneath that on your packet, you have this problem. Guided example 3.9. So it says, a park ranger driving on a back country road suddenly sees a deer, frozen, in the headlights 20 meters ahead. Why it needed parentheses there, I'm not really sure. But, sorry, quotation marks. Yeah, that it was figuratively frozen, not literally like an ice cube. So, okay. I mean, they'd be deceived, but probably not for the deer who's frozen. That probably wouldn't be very fun, I imagine. Yeah. The ranger, who is driving at 11.4 meters per second, immediately applies the brakes and slows with an acceleration of magnitude 3.80 meters per second squared. How much distance is required for the ranger's vehicle to come to rest? So, first things first, right? Establish this pattern. What are we looking for in this problem? If it says how much distance, not final velocity, final position, right? So, XF is our unknown. Where does this ranger's car end up, right? If it's asking us about distance, it's asking us about position, okay? All right, let's go obvious stuff first. So, one obvious thing, Brett, the acceleration, okay? So let's go, acceleration is equal to 3.80 meters per second squared, okay? Next obvious thing, Brett, go ahead. The which velocity? Okay, this velocity that's listed here, right? Velocity initial is 11.4 meters per second. Okay? Now, Simran, here's this time when we have to make sure our signs match up, okay? Physically, what's happening to the Ranger's vehicle in this problem? Slowing down, right? So what has to be true about velocity and acceleration if something is slowing down? Not necessarily acceleration has to be negative, but velocity and acceleration have to have what? Opposite signs, right? So we don't necessarily have to call acceleration negative, but it depends on what we call velocity, right? In this case, they kind of set up the coordinate system with the arrow pointing towards the right, and we said that that's their way of signifying the positive direction. So if that's the case, the Ranger's initial velocity would have what sign? Because it's positive because it's going to the right. So this is going to be positive. That was terrible. But if that's the case, what sign would acceleration have to have? Negative because it's slowing down. Okay? So sometimes we can pick and it doesn't matter, but other times it does. This is one of the cases when it does matter which signs we pick. Okay? All right, so we got that. All right, now let's go with some less obvious information. What less obvious information do we have? Brett, go ahead. Final velocity is going to be what? Because what is it? 0, because what does it tell you happens to the Ranger's vehicle? Comes to a rest, right? Even though it doesn't specifically say V final equals 0, that's what V final equals 0 means, comes to rest, right? And then, another thing that we can sort of assume here, right? At least is that a hand, or you just kind of like... What's one more thing that we would have to kind of make an assumption about in this problem? Let's not go with change in position, because we know that we're looking for final position, but to figure out the change, we have to know what? The initial position, which in this case, our lives are easier if we call initial position what? 0. So the spot where the Ranger steps on his brakes, if we call that 0, that makes our lives easier. Okay? Good there. Brett, good. The 20 relates to what? What is that 20 meters telling you about? Not exactly. The 20 is relating to which object in this problem? The deer, right? None of these numbers are related to the deer, right? So that's a number that we don't need to find out how far it takes the Ranger's vehicle to come to rest, okay? We'll use it a little later to interpret our answer, but we don't need it because the 20 relates to the deer, while the rest of these numbers relate to the Ranger's vehicle. All right, so we just learned VF squared equals VI squared plus 2A x final minus x initial. Again, based on the values that we've picked or what they've given to us, a couple of things can go away in this equation, right? We learned that the final velocity was 0, so that term just becomes 0. And the initial position is 0, so that becomes 0 as well. So then this equation then simplifies out to 0 equals VI squared plus 2A x final. Yep, good. Here, we're trying to solve for something that isn't by itself in the equation, so we have to get it by itself. Whether you put numbers in first and then rearrange, or whether you rearrange with the letters, I don't really care, as long as you get to the right answer. I'm going to rearrange the letters to get x final by itself. And to do that, does that make sense? That's negative VI squared, because I had to bring it to the other side of the equation, right? So I subtract VI from both sides of the equation, okay? And I end up with that equation to solve for x final. And when you plug those numbers, the numbers that we got out of the problem, into this formula, right? Anybody got the calculator? Yeah. I know, I'm asking a lot out of you, right? Yeah, 17.1, is that what it turns out to be? So, I think it is 17.1 if I remember right. So the final position is 17.1 meters. And this would come out to be positive, right? Even though we have a negative acceleration, because when we brought VI from this side of the equation to that side of the equation, we had to subtract it from both sides. So we end up with negative divided by a negative, and it turned out to be positive. So, good news or bad news for the deer? Good news, right? It only takes the Ranger's vehicle 17.1 meters to stop, but that deer is 20 meters ahead. So, he's good. Good there. All right, at the very bottom of page 4, you have table 3.3, which is going to be an important table, not just for tomorrow or for the next week or so, but basically for the rest of this part on mechanics, because while kinematics is the beginning of our study of mechanics, it continues the whole way. So as you can see here, table 3.3, constant acceleration equations of motion. Depending on which book you read or which, text you have, whatever it might be, sometimes you will see these referred to as kinematic equations. Why? Because they just tell us what's going on, but not why it's happening. They relate all of the things that show up in our descriptions of motion and how if we change one, other things change, etc., etc. But if you also look, you will find that in each one of them, you're missing one or more than one of the kinematic descriptors, right? In the top one, we have v initial, we have v final, we have acceleration, and we have time, but there's no mention of what in that equation? Position. Doesn't show up anywhere in that equation. Here, right, x final, x initial, v final, t, what doesn't show up? Acceleration doesn't show up anywhere there, right? We already talked about in this one that v final doesn't show up anywhere, and then this one here, time doesn't show up anywhere. So there's always something's missing, and that's okay. As long as we have what we're looking for and what we know, we can pick the appropriate equation to solve for what we're trying to figure out. Okay? All right. So, homework. Homework. Couple of problems from the end of section 3.2, and then a couple of problems from the end of chapter 3, dealing specifically with the equations that we introduced today, not the ones that we introduced on Friday. Tomorrow, we will do a problem set that incorporates all of them together, just to give us some practice with identifying what are we looking for, what do we know, what equation should we use. All right? Good there? Answers already posted, so if you need to look for answers for those problems, they're there for you.